Hello friends, I welcome you in lecture number 2 on vector calculus. In previous lecture we have talked about gradient and divergence. We recall the definition of a divergence of a vector field. We know that if f bar is a vector field whose components are f1, f2 and f3, then divergence of this vector field f bar is given by partial derivative of first component f1 with respect to x plus partial derivative of second component f2 with respect to y and partial derivative of third component with respect to z. And using this definition we are going to discuss this question which was asked in GTU Winter 2019 exam for 7 marks. So first we understand what is question about. Let r bar equal to xi plus yj plus zk, that is r bar is a position vector and small r is the notation for the length of this vector r bar, and we know that if r bar is x, y, z, suppose components of r bar are x, y, z, then its length is denoted by small r and is defined as square root of square of each component and their addition. That is, length of r bar or magnitude of vector r bar equal to square root of first component square plus second component square plus third component square. So this r, small r, which is a length of vector r bar, is a scalar function. So that is the notation for small r, and it is given that a bar is a constant vector. Constant vector means its components are constants, and using this information we have to find the value of divergence of cross product of this constant vector with position vector r bar divided by nth power of this r, that is r is the scalar function. So to obtain this divergence of this vector, first we will decide what is this cross product a bar cross r bar, then we will multiply it by 1 by r raised to n. Before that, because it is given that a bar is a constant vector, we assume that a bar equal to a1i plus a2j plus a3k, where this a1, a2, a3 are constants. Now we obtain cross product of a bar and r bar using the definition of cross product. It is given by this determinant. First row is unit vectors ijk, second row is components of first vector a bar which are a1, a2, a3, and the last row is components of r bar which are x, y, z. And then we expand or we evaluate this determinant. So we consider this I, vector I, and we consider this first row and first column deleted, and this I, vector I, is multiplied with determinant of this 2 by 2 matrix which is a2z minus a3y. Similarly we consider minus j, and we will not consider the row and column in which this j is present, and we will take determinant of this matrix a1, a3, x, z, that is a1 into z minus a3 into x, that is multiplied with vector j. And similarly this last vector plus k, so we consider this elimination, and we consider multiplication of vector k with determinant of this matrix which is a1y minus a2x. And now we divide this function which is cross product of a bar and r bar by r to the power n. So each term or each component is divided by r raised to n. Now we are interested in the divergence of this quantity, and that we have written in this form, vector form. First component is a2z minus a3y divided by r raised to n. This is second component. And third component, and we are interested in the divergence of this vector f bar. So by definition, divergence of this vector will be equal to partial derivative of this first component with respect to x plus partial derivative of second component with respect to y and plus partial derivative of third component with respect to z. So that I have written here. Del by del x of a2z minus a3y divided by r raised to n plus del by del y of second component, which is a3x minus a1z by r raised to n, and del by del z of a1y minus a2x divided by r raised to n. And we can see that here first derivative is with respect to x. So because it is partial derivative, we will consider y and z as constants. Therefore a2z minus a3y is considered as constant while differentiating with respect to x, and this r raised to n is a function of xyz. We know that small r is square root of x square plus y square plus z square and to the power n. So r is a function of xyz, and we are interested in the partial derivative of r raised to n with respect to x, and r raised to n is in the denominator, so that we will write as del by del x of r to the power minus n. So here a2z minus a3y is considered as constant into partial derivative of 1 over r raised to n with respect to x, that is partial derivative of r raised to minus n with respect to x. So I have taken a2z minus a3y outside this bracket because y and z are considered as constant while differentiating with respect to x. Same thing here derivative is with respect to y, so x and z are considered as constant, and these a1, a2, a3 are constants because vector a bar is a constant vector. So this is outside, and partial derivative of r raised to minus n with respect to y, so that I have written here. Similarly here derivative is with respect to z, therefore a1y minus a2x is considered as constant and into del by del z of r to the power minus n. So now our focus is to obtain these values, partial derivatives of r raised to minus n with respect to x, y and z, and we know that r raised to minus n is a function of x, y, z. So directly r raised to minus n is a function of r, and indirectly it is a function of x, y, z. So we can say that r raised to minus n is a composite function of x, y, z. So to obtain this partial derivative of r raised to minus n with respect to x, we have to apply chain rule. That is, first we differentiate this function with respect to r, and in the product we will find out del r by del x. So first we will require this quantity del r by del x. So for that we use this definition of length of r bar. R bar is xi plus yj plus zk. Therefore its length is small r equal to square root of x square plus y square plus z square, and if we square on both sides we have r square equal to x square plus y square plus z square. And now I am interested in the del r by del x. So for that I differentiate both sides with respect to x. So I have to differentiate r square with respect to x. So this I can write as, because r square is directly a function of r, I have to first differentiate with respect to r, and in the product I have to write del r by del x. This is by chain rule. So using chain rule we differentiate this equation with respect to x on both sides. Therefore we have 2r into del r by del x. Here we are applying chain rule, equal to derivative of this quantity with respect to x. Derivative of x square is 2x, and these two are considered as constant, therefore their derivative is 0, and we have 2r times del r by del x equal to 2x, and this 2 will cancel out, and if we transfer r on right hand side, we have del r by del x equal to x divided by r, and our focus is to obtain the value of partial derivative of r raised to minus n with respect to x. So here also we will apply chain rule. First we will differentiate r raised to minus n with respect to r, and in the product we will write del r by del x, which we have obtained as x by r. So that I have written here. This is by chain rule. Partial derivative of r raised to minus n with respect to x equal to partial derivative of r raised to minus n with respect to r multiplied with partial derivative of r with respect to x. Now this is going to be minus n times r raised to minus n minus 1, and del r by del x we substitute as x by r, and then we combine these two. Here power of r is 1, so this is going to be r raised to minus n minus 1 minus 1, that is r raised to minus n minus 2, and this we can rewrite as r to the power, we take negative sign common, in the bracket we have n plus 2, and this again we can rewrite as minus n into x divided by r raised to n plus 2. So this is partial derivative of r raised to minus n with respect to x. Now if you observe that this r raised to n is nothing but x square plus y square plus z square raised to n by 2, and if I consider minus n, I will have minus n by 2. So you can see, if we interchange these variables, if we replace x by y and y by z, or if we interchange x and z and x and y, then this function will not change. That means it is symmetric function in x, y, z, or we can say that r raised to minus n is symmetrical in x, y and z. That is, if we replace x by y and y by z or any other combinations we do, then function will not change. Function remains as it is by interchanging these variables. So that type of function is called symmetrical function. So here r raised to minus n is symmetrical in x, y and z. So using this fact, we can write down two other partial derivatives with respect to y and x simply by interchanging this variable. If we are interested in del by del y, here x will be replaced by y, and if we are interested in del by del z, this x will be replaced by z. So that we can directly write down, since r raised to minus n is symmetrical in x, y, z, we obtain that partial derivative of r raised to minus n with respect to y equal to minus n into y divided by r raised to n plus 2, and if we are interested in the partial derivative with respect to z, instead of y we will put z. So using this symmetrical function, we have written these two other derivatives. Now we use all these derivatives of r raised to minus n in equation number 1. We are interested in the divergence of this vector. So now we have obtained these values, so that we substitute here, we keep all these brackets as it is. So using equations 2, 3 and 4 in 1, we will obtain this expression. Okay, these brackets are as it is, and we have written partial derivatives of r raised to minus n with respect to x, with respect to y and with respect to z. Now in all these quantities, you can see this quantity is common in each term, negative of n divided by r raised to n plus 2. So that I will take common, and I will multiply this bracket by x, this bracket by y, and this bracket by z. So if I take this quantity outside, and I will have a2z minus a3y into x. So I will have a2z into x minus a3y into x. Similarly, this bracket is multiplied with y, so I have a3x into y minus a1z into y. Here this bracket is multiplied by z, so I have a1yz minus a2xz, and all these terms are in the addition, and we have taken this minus n over r raised to n plus 2 common. So I will obtain this expression, and now you can see I have a2xz here and negative a2xz here, so that will cancel each other. Similarly, a3xy minus a3xy, so these two will cancel each other, plus a1yz negative a1yz, so you can see divergence is 0. So therefore divergence of this vector a bar cross r bar divided by r raised to n is 0. So here we have simply used the definition of divergence, and we have used the fact that this vector a bar is a constant vector. So this is very easy question, and it was asked for 7 marks. You can see first I have written the expression for constant vector a bar, and I have written that these a1, a2, a3 are constants. Then I obtain the cross product of a bar and r bar using the definition of cross product or vector product. Here I am simply using the expansion of determinant. Then I divide this by r raised to n, and after that I am using simply the definition of divergence. And to obtain all these derivatives, we are using chain rule. First we obtain del r by del x, and then here we apply chain rule, and then using the symmetry of r raised to minus n, we obtain two other derivatives, and by substituting all these values we find that divergence of this vector is 0. So this is all about this session. We will continue with these lectures on vector calculus in upcoming days. Thanks for watching.